Welcome to the Make the Connection series. This video has been prepared to help students to make the connection between lecture and laboratory experiment. It is about reviewing some of the theory from lecture and checking and performing some section of these lessons in lab. Today's lab experiment is enzymatic activity, a couple experiment of reaction to carry out in order to determine the activity of some enzymes. In lecture, we studied proteins. They are large biomolecules made up of many amino acids linked together through peptide bonds. In this example, a glycine reacts with cysteine to yield a dipeptide glycylcysteine. The amide in red color is the peptide bond binding together the two amino acids. Proteins can be classified in 7 categories. Hormone proteins, example insulin secreted by the pancreas, facilitating the use of glucose for energy generation. Storage proteins, example myoglobin that stores oxygen in muscles. Transport proteins, example hemoglobin, the oxygen carrier in the blood serum. Structural proteins, example alpha-keratin, the main components of hair or nail. Protective protein, example immunoglobulin that aids in destruction of invading bacteria. Contractile proteins, example actin and myosin that govern the muscle movement, and then the enzymes, example amylase that begins the digestion of carbohydrates. Enzymes are catalytic proteins. A catalyst is a substance that speeds up chemical reactions. In the absence of enzymes, reactions would not take place at sufficient speeds to sustain life. Enzymes are characterized by 2 properties. 1. They are extremely specific. That means a given enzyme will only catalyze one type of chemical reaction. 2. They are very effective since they can increase the rates of reactions by 1 billion times to millions of billion times, depending on the type of reaction, the site where it occurs, and the time the product is needed. To make an analogy, suppose that there is a baby boy born in the year 2010. This baby will grow up, becoming a child, a teen, a young man. He will attend schools and colleges, he will work and have a career, and he will eventually retire. After a while, he will be celebrating his 100th birthday. So, the rate of reaction to change the baby to an old man is about 100 years. If there was a magic catalyst equivalent to a specific enzyme, that would speed up the lifetime of this person. The time of 100 years will be reduced to only 3 seconds. How do we explain this rate change? Here is a graph representing the energy versus the path of reaction. The reaction is reactant A yields product B. Case without catalyst. The reaction shown here is an exothermic process since the enthalpy change is negative. In the other hand, the reactant A must absorb a certain amount of energy called EA, or activation energy, and changes to an excited state A star, also called transition state A star. Then this transition state yields the product B. In the presence of catalyst, the catalyst lowers the activation energy. The curve is changed from the red color to the teal blue color. The excited state A is reached just after the reactant A absorbs the amount of energy shown in the red arrow. That has no effect in the enthalpy change, but speeds up the reaction. As we stated before, that may go easily at least by a billion times the initial rates. So the activation energy in a catalyzed reaction is reduced. Two factors will be determinant for the enzymatic activity: temperature and pH. The temperature of a human body is 37 degrees Celsius, and so is the temperature inside cells and different organs where reactions take place. The graph shows an optimum activity at 37 degrees Celsius. This activity decreases below or above that temperature of 37 degrees Celsius. The blood fluid in the body has a pH 7.4. The pH of most sites in the body equals 7.4. The graph shown here tells us that the enzymatic activity is optimum when the reaction occurs at pH equals 7.4. In the contrary, in the stomach, for example, where the pH is very acidic because of the presence of hydrochloric acid, the optimum activity should be around pH 1.5. The purpose of this lab experiment is